Hello, everyone. Okay, I think people are still coming. So, yeah, good morning and good evening, depending on your time zone. Thank you very much for being in this masterclass. My name is Panos Alexopoulos, and today's topic will be about natural language processing and knowledge graphs. So let me share my screen as people still coming. Okay, I hope you can see my screen. So, a brief introduction about me. I've been active in the area of semantic technologies for around 15 years, both as a researcher and as a practitioner. And since 2016, I've been working as head of ontology at Textkernel. Textkernel is a Dutch company that builds software for semantic matchmaking between people and jobs. And my role there, my team, is responsible for developing and delivering a large cross-lingual knowledge graph in the HR and recruitment domain. And part of this work relates to the automation of the construction process of the knowledge graph, hence this masterclass. Also, last year I published a book that summarizes more or less my experiences in the field, and it tries to cover the complete life cycle of knowledge graphs with particular focus on how we apply it in the so-called wild. So, what we're going to talk about today. Today we're going to talk about knowledge graphs. My assumption is that most of you know already what a knowledge graph is, or at least have a rough idea. But we will try also to clarify the term, and if there are any questions, I'm happy to answer them and clarify things. Most importantly, I'm going to talk about how to use natural language processing for building knowledge graphs, for automating and scaling the construction of knowledge graphs. So knowledge graphs, so the relation between NLP and knowledge graph is symmetrical, let's say. So on the one hand, we can use knowledge graphs to facilitate NLP tasks, like, for example, entity detection or summarization or relation extraction. And vice versa, we can use NLP tasks in order to build knowledge graphs. So the focus of today's masterclass will be on the one direction, the direction from raw data, raw text, typically, to structured knowledge. And this masterclass has two parts, and each part will last around 2 hours. In the first part, we will have 2 sessions. The first session will be about knowledge graphs in general, so it will be like a fast introduction into knowledge graphs, what they are, what are their main characteristics, and what we should be mostly care about, what it means to develop a knowledge graph, what are the typical steps, what are the difficulties in building a knowledge graph, what are the elements a knowledge graph consists of, and then how we want and how we pursue to mine these elements from text. In the second session, we're going to focus on the problem of entity mining. So we have a knowledge graph. A knowledge graph typically contains entities and relations. Session 2 will be about how we mine entities, how we discover in an automatic way entities from text. We're going to use Spaces. Space is an open source NLP toolkit, and we're going to see how we can use its pre-trained NER models, how to write custom extraction rules, but also how to customize the models with additional examples and additional entity types that we might have in our domain or application scenario. In the second part, and in session 3, we're going to consider the problem of mining relations. And there we will see a new technique, a relatively recent technique, which is about adapting and using sentence embedding. So it's related a lot to deep learning neural networks. Of course, we're going to see it in a relatively high level. We're not going to go very deep. It will be very practical, but and methodological. But I think it will be really useful and insightful what we're going to see. Finally, in session 4, we're going to discuss some methodological aspects of that we need to consider when we think of a solution, of an NLP solution for a knowledge graph. So, for example, what should be the order of the mining steps? What should be our starting point? Should it be the data? Should it be the tasks? Should it be the knowledge graph? How to define the ground truth? But we need to be careful when we define the ground truth against which we're going to evaluate these NLP systems. Also, how we select data sources, what we need to consider when we select the data from which we're going to mine the knowledge graphs. How we evaluate the result, and that includes also something that I like to call adversarial evaluation. So an evaluation whose aim is not just to see how good the system is, but also how bad it is. Not in order to, let's say, badmouth it, but in order to understand where its flaws are and where should we be really careful about. I will try to make this as much as possible interactive, so there will be frequent Q&A slots within the session in the end. So at some point, I will say, okay, now we have a Q&A slot. Please write your questions in the chat, and I will try to answer them. But of course, if you have an urgent or important question, please raise your hand, and Elias, who's the moderator, will interrupt me, and then I can answer the question. The slides will be available after the masterclass, so I will make sure to share them with Elias, who's going to send it to all the registered participants. The hands-on sessions have the form of Python notebooks in the Google Colab environment. So the reason I chose this environment was that it has the least effort to set up. So it already has a lot of libraries in there, so it's much easier to use. So when we start the hands-on sessions, I will share with you in chat the link to the Colab notebook that I'm going to be using, which please copy it if you want and use it, and use your own copy if you want to follow what I will be doing. In any case, you can then use it also as a reference after the masterclass. So, any questions so far? Okay, maybe then I have a question for you.
Panos, just to let you know that people are typing. Let's give them a second or two. Good so far, some say.
Yeah.
But,
nice.
Because from what I understand, when you handle the screen share, you have no direct visibility, so I can relay all chat info to you.
Okay, so then I have a question for the audience, which is about your experience with NLP systems. So, if I may, my question is, how experienced are you in using or developing NLP systems? Not necessarily for knowledge graphs, but in general, right? I can already tell you that I consider myself at best, between beginner and intermediate. So I'm not really a deep expert, especially when it comes to the underlying algorithms. So anyone who's advanced, please excuse me already for any, and correct me if I say something that is really wrong. I will try to keep this, what we're going to discuss today, as high level as possible and as practical as possible. Okay, so I can see that the majority, the vast majority is beginners, so that's okay, that's fine, it's great actually. So let's begin. Let me share my screen again. Okay, let's start with some knowledge graph basics. There are many definitions out there about knowledge graphs, but the definition I prefer is that knowledge graphs are interconnected entities under shared semantics. Now, it's not something really new. It's not a term, although it's a term that it's very popular, has been very popular the last, I don't know, 5 to 10 years, especially after Google in 2012 created its own knowledge graph on the web and really popularized the term. The notion, the concept of a knowledge graph is not really new, right? It's rather a rebranding of terms like semantic networks, knowledge bases, ontologies, linked data. So things that we have seen even from the late 80s, early 90s. And if you have been designing database schemas, taxonomies, ontologies, or other types of structured data, then you already know a lot about knowledge graphs. So in terms of what a knowledge graph is, there's not much surprise, I would say. However, what I think is an important characteristic of a knowledge graph, an important part of its definition, is the shareability of the semantics. And why is that? So when we talk about knowledge graphs, we may discuss about things like its representation. So we talk about RDF, or we talk about property graphs, Neo4j, or other formats, JSON, LD, NoSQL, and any other way by which we can structure a knowledge graph. We can talk about how big or small is the knowledge graph and how interconnected it is. We can talk about its scope and domain. Is it about a single domain? Is it about multiple domains? We can also talk about its purpose, if we use it for data analytics, data integration, question answering. And we can also discuss about what elements it contains. Does it contain concrete entities, real-world entities? Does it contain taxonomies? Does it contain associative relations? All these are really important dimensions of knowledge graphs, and we really need to be aware of them when we start a knowledge graph project, a knowledge graph initiative, let's say. However, for me, the crucial dimensions of knowledge graphs are, first, the accuracy of meaning. So knowledge graphs are meant to communicate meaning, to represent explicitly and communicate meaning. Therefore, whatever statement, whatever assertion is in the knowledge graph needs to be as accurate as possible. So it needs to be true and it needs to be accepted by all people and systems that use the graph. Second, the meaning should be explicit, right? It should be clear for anyone who consumes the graph what its entity, relation, or other element means. If that doesn't happen, if it's unclear, then the quality of the knowledge graph with respect to explicitness is low. Finally, whatever assertions we make in a knowledge graph has to be commonly acceptable among, again, those who use it. Right? So, to give you an example, at XKernel we have a knowledge graph that relates professions and skills. And in this graph, we have a relation between a profession and a skill based on which that suggests that a skill is important for a given profession. Now, the risk with such a skill is that it may be that for a particular industry or for a particular country, a skill may be important for a profession, but in another industry, the same thing may not be true. So in that case, we won't have agreement if we suggest that this assertion between the profession and the skill is globally true. And this when we violate all these three dimensions, let's say, when we don't make sure that the quality of these 3 dimensions is high, we end up with a semantic gap. The semantic gap between those who use the knowledge graph and those who develop it, those who put the content in there. Now, there are both objective and subjective enemies, as I call them, of accuracy, explicitness, and agreement. On the one hand, we have ambiguity, right? In our language, we very often use the same term, the same word, the same phrase to denote different meanings. That's a challenge that is also very important in the field of natural language processing. And it's something that we will see that as a challenge when we construct knowledge graphs, both through experts manually, but mostly through when we analyze texts. The second enemy is diversity and variety. So in ambiguity, we have the same term having different meanings. In diversity and variety, we have the same meaning represented by many different terms, by many different ways. That's also a problem. There's also a challenge that we need to tackle when we develop knowledge graphs. Third, we have vagueness. Vagueness is when we have concepts and relations whose truth conditions are not explicitly known or agreed among people. One example is, for instance, the essentiality of the professions of a skill for a given profession that I just mentioned. But in general, when you see terms like near, average, large, critical, strategic, rich, all these are vague terms for which we rarely have an objective definition, an objective truth condition. Fourth, we have semantic change. Semantic change is the phenomenon where the meaning of particular of our language, of particular terms, changes over time, right? Some domains, some concepts are quite volatile and change much faster than quite fast. Some others not so much. But in any case, we have change, and this change means that our knowledge graphs are not static artifacts. They are rather dynamic artifacts that it's not enough to build them once. We actually need to maintain and evolve them. Finally, our last enemy is ourselves. Ourselves, I mean the developers of knowledge graphs. And it's about when we do bad modeling. And this is something that I try to extensively cover in my book. And today I'm going to describe some, in the last part of the masterclass, in the 4th hour, some pitfalls where we fall into when we develop NLP solutions for building knowledge graphs. Now, something that I'm often asked by people when I say that my job is to develop a knowledge graph, they ask me, okay, is that easy? How easy is to build a knowledge graph? And my answer there is usually a story. It's a story, it's a tale of 2 graphs. The first graph was developed between 2012 and 2017 by the European Commission, and it's in the domain of the labor market. So it's quite similar to what we do at TextKernel. It's called ESCO, which stands for European Skill Classification and Occupations. And it's a graph that consists of around 12,000 skill concepts and 3,000 profession concepts, which are interrelated to each other and which are available for 27 languages, for the 27 languages of the European countries. It has been built completely manually by experts in 6 years, and it cost around 15 million euros. And currently, since 2017 that it was released, it is updated around once a year by maintenance committee, and the updates are relatively small. So we're talking about changing maybe 50 to 100 concepts maximum per year. So it's not a graph that really changes over time. On the other hand, we have DBpedia. DBpedia, I also assume that most of you know what DBpedia is, but in case you don't know, DBpedia is a knowledge graph that is derived from Wikipedia. It was first released in 2007, and it's automatically extracted from Wikipedia info boxes. So there is a fully automatic approach that parses the info boxes of Wikipedia pages, not the main articles, just the info boxes, and extracts entities and relations from there. It currently has more than 17 million entities in 127 languages. And it has a live version, and almost every month a new version is released. So you see the big difference here. On the one hand, we have a very small graph of a couple of around 15,000 constants in overall, which is quite expensive, and it's really slow in evolving. And on the other hand, we have a very fast knowledge graph, a very evolving knowledge graph, a very big one, that it's definitely much cheaper to maintain. So why the difference? Right, why the difference? Did the European Commission, was the European Commission stupid in spending all this amount of money to build the graph? The difference lies in the following factors. First, we have what we call the abstraction of entities. Abstract entities, as we will see.
Panos,
yes?
I don't know if you want me to interrupt you when someone raises his or her hand to relay the question, or to just start.
Yes, if there is a raise of hand, please interrupt me, yes.
Yeah, there is a question, I think, from Aftab. We call ESCO a taxonomy or a knowledge graph. If ESCO doesn't have instant data, can we still call it a knowledge graph?
For me, yes. I mean, yeah, it's about the terminology. I understand what you're saying. I like to call it knowledge graph because it has concepts, it has, or entities if you like, and it has relations, both taxonomical, both hierarchical, and across occupations and skills. So in my mindset, it's a knowledge graph. But also, it's not that the distinction is not that critical for the purposes of what we do here. Okay. Okay. So one big difference between the two graphs is that the ESCO graph has to deal with abstract entities. Professions and skills can be quite hard to really define in a clear and crisp way. So for example, if we spend the next 3 hours trying to define exactly what a data scientist is, right? What skills should they have? What exactly is their job? How they are distinguished between business analysts, between statisticians, between natural language processing engineers, and things like that, we will never finish. Right? So there's a lot of debate and a lot of disagreement about this. On the other hand, if we try to define the country, the Netherlands, this is quite straightforward what it is, right? And Wikipedia, in its majority, is about concrete entities. And actually, when it comes to abstract entities, it has big quality problems that we've seen. The second factor is the vagueness of the relations, right? So as I mentioned earlier, vagueness is about not having crisp truth conditions. And in that case, it's also very hard to define and achieve consensus even among experts. A third aspect, which is very related to this masterclass, is the available data sources. So Wikipedia is based on, is mined automatically from Wikipedia info boxes, which are semi-structured information, right? It already has a structure, and it's quite convenient and quite accurate to get information from. On the other hand, for ESCO didn't have available a lot of data that could, and methods that could enable the automatic extraction. And I can already tell you, because at XNL we try to do something similar. We try to mine professional skills from CVs and jobs. It's a quite hard task. It's a task that it's not easy to fully automate and say, okay, I will just have an NLP pipeline that will do this for me, and there's no need to have any human input whatsoever. Finally, it's about quality. ESCO, because of political issues, because of the importance of the domain and the importance of the application scenarios, because remember, in the end, it's about employment, it's about facilitating employment, wanted really very high accuracy and trustworthiness of the model, right? Whereas the Wikipedia, it's open, it's free, it's okay if it has some errors. It's not such a critical resource when it's applied. In general, the difficulty factors that we face when we build a knowledge graph has to do with the clarity of semantics, right? So in general, abstract and vague entities and relations are harder to define and populate. Second, the availability, structure, and appropriateness of data to automatically derive the graph from, right? So it's important that we have input data that are relatively structured, which is not the case, and which are available. The maturity of methods and tools, so how effective and usable are algorithms and tools for automatic knowledge constructions. And we will see a bit later for the tasks of entity mining and relation mining that some of the state-of-the-art tools that are out there at the moment are, for some particular entities and relations, are not so effective. Fourth, the quality requirement strategy. So which quality aspects are more important and to what extent? Do we care more about accuracy in our knowledge graph? Do we care more about coverage and recall? And finally, when the knowledge graph is built within an organizational context, the structure of the organization, the management practices, or the engineering practices can really affect the way the knowledge graph is developed. The main thing to have in mind when you start or when you enter a knowledge graph project is that it's almost never a one-off and purely technical engineering project. It's not one-off because the graphs we build require a continuous effort to keep them relevant and useful, exactly because of the semantic change phenomenon. And it's not purely technical engineering because we have to take into account business, strategic, and organizational aspects. In my book and in all these years of my experience, I try to, I know that there are a lot of methodologies out there that outline the steps that you need to take when you start developing a knowledge graph. I also try to create an execution framework, let's call it like that. And then I try to make it as high level as possible. So when you consider a knowledge graph initiative, right? First, it's important that, as I say, you know what you're getting into, what you're signing for, right? So what are knowledge graphs, who builds them and why, and is it easy to build one? So all this knowledge that we saw, so that we can avoid things like, yeah, it's easy to build a knowledge graph in 2 months, right? Or it's all we need is a fancy graph database and that's it. Setting up the stage. Specifications. What are we building? Why are we building it? Who is building it? Right? This is applicable in every IT project and every engineering project, of course, right? But it's also important here. Giving it a shape, schema design, but also giving it a substance. And this is what, again, this masterclass is about. It's about how we can populate the knowledge graph with entities, with concepts, with instances, and how we can scale that up, right? The substance of the knowledge graph. So we may have 2 or 3 entity types. ESCO, for example, has only 3 entity types, 3 classes. It has profession, occupation, and qualification. So the substance is in the concepts themselves. And that's why actually, in the previous question, that's why I consider it a knowledge graph, right? Because for ESCO, the instance data are the skills themselves. So we have the class skills, if you like, and we have the skill, for example, data science, which is an instance. So in that sense, it's a knowledge graph. If we take the definition that a knowledge graph needs to have instance data. Of course, we have quality assurance, right? Application, make it useful, and evolution, make it last. So today it will be about the substance part, right? About how we can utilize some basic NLP tools in order to give substance to a knowledge graph. Before we start considering the automation of building a knowledge graph, we need to understand what we need to build, right? What elements we need to construct, what elements we need, to extract from text. So for starters, we have entities and concepts, right? Without being too philosophical, an entity is something that may exist concretely or abstractly outside or within our mind. And abstract entities are also usually called concepts and are typically more difficult to model than concrete ones, right? So in the discourse about knowledge graphs, we tend to talk about people, persons, right? We talk about buildings, about locations, about organizations, which are rather concrete entities. But we also may have abstract entities, like, for example, object-oriented programming or rock music. So we can have film genres that are rather abstract, or we may have political ideologies that are also abstract. So the distinction is important, not because we need to make it explicitly in a knowledge graph, but because knowing what kind of entities we expect to have in our knowledge graph, whether they are mostly concrete or mostly abstract, we can somehow predict the difficulty that we will face when we start developing it. Now, in some frameworks, entities are separated between classes and individuals. So classes are abstract entities that represent kinds of things in the world, and they may serve as semantic types of other entities, concrete or abstract. So for example, we can take the concept of building, and we can say it's a class and its instances are concrete buildings, specific buildings of the world, like the Empire State Building, right? The same can be said for dog, computer, etc. And in that case, the entities that belong to a class are also known as instances or individuals. And if you're coming from the semantic web community, and you've been familiar with RDF and all, their entities are organized indeed into class individuals. But there are also other representation frameworks where this distinction is not made. SCOS, for example, the Simple Knowledge Organization System, considers all entities are instances of the class SCOS concept, and it doesn't care about the distinction between a class and an instance among its concepts. Of course, we also have relations, right? A relation is quite straightforward. It expresses a particular way that two or more entities can be related to one another, right? So this is an example of relations found in the ESCO knowledge graph. So we have occupation and skills, and they're related. We have the relation between a skill being essential for an occupation or being an optional for an occupation. And we may also have a skill being broader than another skill. So someone may say that Java development or Python development is a narrower concept, a more specific concept than computer programming, for example. In knowledge graphs, we may also have attributes. If the attributes are about entities, then they represent characteristics of the entity that we cannot or choose not to represent as a relation with another entity, and instead we use literal values. Because practically, the conceptual distinction between a relation and an attribute is not always clear and ends up being a matter of representation choice. So, for instance, in this figure here, you can see a knowledge graph that says that we have a person, an entity John, who is a person, whose age is 27, and he's friends with Sally, who's also a person, and they're friends since the first of December 2013. And they both have read a book whose title is Graph Databases, and the authors of that book are Jim Weber and Ian Robinson. Now, the interesting thing here is that you can see that the authors of the book are not other entities, but are attributes. They are not relations with other entities. So that means that we don't have any additional information about Jim Weber or Ian Robinson. They are not distinct entities. They are not modeled as relations, they are modeled as attributes. So this is a choice. This is a representation choice. It can also be, although it's a bit rare, to have in knowledge graph complex axioms and rules. usually in formal ontologies you have that a lot. And in general, these are complex elements that allow the modeling of more elaborate data semantics and, most importantly, to enable reasoning. So, for example, in OWL, ontological, we can define that a person A is the uncle of person B if he's the brother of some A's parent. One very important element in a knowledge graph, and in ontology in general, but also in knowledge graphs, is the lexicalizations. And it's what makes the difference between what Google says between strings and things, right? So a knowledge graph is meant to contain conceptualized knowledge, semantic knowledge. That means that it doesn't model strings, doesn't model terms without meaning. It models entities and concepts. And lexicalization is the process by which we link a model element, an entity, a relation, or an attribute to one or more terms that can be used to express it in natural language, right? So, for instance, we have the concept of shrubs, which in English, one of its names, one of its lexicalization is shrubs, but it also has a synonym, which is called bushes. And in French, it has also two lexicalizations. One is called arbuste and the other boisson. And why is that important? Because knowing usually this knowledge, the reason we put it in a knowledge graph is, on the one hand, to make the meaning of the entity or of the concept more explicit and more understandable by humans. But also when we apply the knowledge graph for an NLP task, right? So if we wanted to detect this entity into a text using the knowledge graph, then it's very useful to know all of its all the ways that it can be expressed in natural language. Vice versa, the challenge we have when we build the knowledge graph is for a given entity to discover and to know all its possible synonyms, all its possible lexicalizations. Another important relation is meaning inclusion. Meaning inclusion is a relation between two elements that indicates that the meaning of the one element is included in the meaning of the other. When this is applied in classes, it's called usually class and relation subsumption. And it's more or less, it has a very important logical implication that if a class A is a subclass of class B, then all entities that instantiate A are also instances of B. So for instance, if we have the class pizza and it has a subclass cheesy pizza, then all instances of cheesy pizzas are also instances of pizza. And the same can be said about relations. But in general, we may have just broader and narrower relation between concepts. And this indicates that one is in some way more general than the other. And this actually, in the taxonomy world, covers three different relation types: instantiations, meaning inclusion, and part-whole relation. So it's very important, especially for people who work a lot with RDF and OL, to understand that a subclass hierarchy is not always equivalent from a semantic perspective to a broader or narrower hierarchy. Also, we may have mapping and interlinking relations. So these are relations that link elements that belong to different semantic models, to different knowledge graphs, right? One example is the all same as, that denotes that two individual entities between different models have the same meaning. Last but not least, we have documentation elements. So we have some elements that aim at more at human understandability rather than machine usability, like natural language definition of an entity, provenance information, scope notes, and things like that. And this is also something that in many cases we want to automatically derive from text. So there is some research in the NLP community that, given a term or an entity, tries to find natural language definition about its meaning. The hour. Okay, so far we've seen the overall life cycle of developing a knowledge graph and what are the elements, what we need to build. So the question now that comes to the problem of mining this knowledge. So instead of asking people to explicitly open an editor and start defining in a top-down fashion entities and relations, instead we want to mine this knowledge graph from raw data, from input data. So the definition we have for knowledge graph mining is that it's a task for acquiring and incorporating terms, entities, relations, and other elements from data, typically text, but it can be also from other semi-structured data, in a knowledge graph with limited human effort, right? Our goal is to have as much as possible limited human effort to ensure the quality of the graph. Now, something important from an NLP perspective is that our goal is not to understand everything that is going on in the source data, but instead is to get from them the elements we need. So, to give you an example, let's say that we have I don't know, a film review, and we want to detect the entities that are we want to detect the actors that are mentioned in that text. This is a typical NLP task, which actually is called named entity recognition. And when we do that, our goal is to find all the actors that are in there in every sentence that they are mentioned. So if, for example, one actor is mentioned 3 times and we only find it once, then our system is not that good because it only found 1 occurrence out of 3, because the goal is to find all occurrences. If, on the other hand, we see the same task as a knowledge graph population task, where our goal is for the class actor to find all the individual actors that exist out there, then even if one review has 3 mentions of the same actor, with exactly the same mentions, all we need is 1. We don't need all 3. So the task formulation is slightly different than the typical NLP task. And this is something that we need to consider when we evaluate systems and methods for such tasks. Now, what are the main mining tasks that we are up against? So on the one hand, we have extracting entities, the problem of extracting entities. Our goal there is to extract terms from text that denote entities and concepts of some particular type, such as persons, organizations, locations, or other. So typically we have a target entity type or class, if you like, that we wish to populate, to find instances of, and we want to find those, to discover those in text. Then we want to do the same for relations. We have a relation and we want to find the pairs or more entities, if you like, if the relation is not binary, that hold between these entities. Synonym is one relation between entities, meaning inclusion is another, semantic relatedness, and any other domain-specific relations that you can think of. Like, for example, the relation capital of between cities and countries. And then there's also the task of mining more complex knowledge. It can be of events or more axioms and rules that can be used for reasoning purposes. Today we will focus on the first 2 tasks, on extracting entities and on extracting relations. Now, how easy or difficult will be the extraction of this kind of extraction depends on a number of things. It depends, first of all, on the complexity of the target semantics. So to give you an example here, if we just want to find salient terms in a text, so what are the terms in a given text that seem to be more important, right? There are quite easy techniques to do that. There is the frequency or the TF-IDF metric. There are things like that. But finding exactly what entities are mentioned there is more difficult task than that. Another difficulty is the specificity of target semantics. In the example that I gave earlier about film reviews, imagine that we want to find mentions of persons. Finding mentions of persons is much easier than distinguishing within the same text between actors, film characters, directors, choreographers, and other roles that people have, right? Why? Because in the first case, the target entity type encompasses much more, a bigger variety of instances than in the second case, and there's no need in the first case of so much subtle distinctions to be made, right? Because in the end, ultimately, the main difficulty in building NLP systems is to discover subtleties and nuance in meaning in texts. Finally, another factor is the availability of appropriate data, right? So, for instance, to look for synonyms or hyponyms of meaning inclusion relations of an entity in a news article is not so easy. Why? Because usually when we write in news, we don't spend much time in defining the entities and trying to say, yeah, this entity, also known as that entity, is so and so. This is usually done in an encyclopedic text, right? And if we don't have that, then it may be more difficult to find the data. Now, in both the research and industry communities, there are several knowledge mining tools that have been developed. Some are more academic, like Pikes and K-tools and Stanford NLP. Some others are more industrial strength, like Spacey and Diffbot. And also some are free and open source, whereas others are paid APIs. Now, from my experience, and please, if anyone in the audience has more knowledge about that, let us know. There are many entity extraction APIs and services out there which work relatively well, but for a limited set of entity types. So more than 90% of these tools are able to identify persons, locations, and perhaps organizations. But it's much more difficult to find a system that will find, for example, actors, or will find skills or professions or entities like that, right? So there is, let's say, an asymmetry between the coverage in entity types of these systems. On the other hand, for relation extraction systems, the available off-the-shelf, as I call them, APIs and services are far more limited. And especially for correlations like synonymy and meaning inclusion, there are very few, I cannot think from my mind any ready to be used system that can find you synonyms and hyponyms. Most of the systems that are out there are experimental and coming out of research, which actually it's an indication how difficult it is to generalize the task, right? How difficult is the relation extraction compared to the entity extraction task. Now, all these systems, right, follow one or more, or a combination of the following 6 mining approaches. The oldest mining approach is to have hand-built patterns and rules. So that is, we go and we define linguistic or syntactical, usually, rules and patterns that allows us to extract information from text, right? I will give an example in the next slide. The main problem with these rules is that they may offer, in most of the cases, high precision, but they have really low recall. So it's really hard to scale and generalize all the different ways that the same piece of information can be expressed. So therefore, it doesn't really solve the problem. It doesn't really solve a lot the problem of automating the knowledge graph construction. The second technique is supervised machine learning. In this case, what happens is that the extraction patterns and rules are learned from human-labeled examples. So instead of trying to define explicitly the extraction rule, we give examples of positive and negative extractions, they are called the labeled examples, and we let the system generalize the patterns that it sees in the data and then apply them in new data that it hasn't seen. There's also unsupervised learning, where the extraction patterns and rules are learned from unlabeled data. So we just take a large corpus of text and we apply some statistical and other machine learning based techniques that allows us to extract regular patterns between language. The most known example of unsupervised learning are the language models, which are famous now, like BERT and similar, right? And GPT-2 and GPT-3. So these are systems that learn regularities in text, between words, between sentences, between phrases, and they use them for various tasks without needing explicit labeling. And we also have other variations like semi-supervised machine learning, where what happens is that we give some few labeled data instead of having a lot of labeled data and a lot of unlabeled data. So the system starts with a few labeled data and then it tries to teach itself based on this data about what happens in the rest. There's also the distance supervision, where the extraction patterns and rules are learned from machine labeled data. So what happens here is that we define a couple of heuristics and rules to label the data, and then we apply supervised machine learning, but not on human labeled examples, but on machine labeled examples. And finally, we have transfer learning, which is a relatively recent technique. And what it does, we will see it in detail a bit later, is that it uses also some labeled data, but it utilizes also existing NLP models that have been trained for another task, for a more general task, usually language models, BERT, word vectors, and things like that. An example of patterns, very famous one, which I don't know its age, but I think it's more than 20 or 30 years now, are the Hirst patterns for easy relations, right? So we can have the pattern X or other Y, or X and other Y, which when applied in a sentence like temples, treasuries, and other important buildings, we can understand that a temple and a treasury is an important building, right? Or when we have the pattern such Y as X, then when in the sentence such authors as Roth or Bellow, we can deduce that Roth and Bellow are both instances of authors. Okay, I think this covers what I wanted to say in this first hour. Actually, we have only 5 minutes until the end of the hour, so I'm open to questions for now.
Panos, there has been quite a round of discussion, and if you could just check the chat and make comments while people are typing their questions or thinking about.
Okay, I see a question here from Max Harper. It says, I suppose it's outside of scope, but I'd love to hear a bit about permissions and privacy with respect to enterprise organizational knowledge graph, as text mining at scale will often run into the issue of Big Brother monitoring and commonly runs into permissions, and nearby to which is internal politics. Yeah, I think I don't have much experience on that, but I think it applies also with knowledge graphs, everything that should apply in any data mining project, right? Where the data come from, what kind of sensitive information they have. This is a problem that we have also in TextKernel, because, for instance, when we mine information from CVs, it's really important that we respect GDPR. So on the one hand, we need to have explicit license from the owners of the CVs that we're good to go. And also in many cases to ensure that the data are anonymized, that effectively anonymized, so that we don't know who they belong to, that we cannot infer information about particular individuals. Let me see. Okay, I see there was a discussion about permissions. Okay. Yeah, I think there was a problem with the slides, with the flow. I see after this typing. Okay, great. So it's 8 o'clock here in the Netherlands. Let's have a 5-minute break, and we will resume with entity mining in 5 minutes from now.
Sure thing.
Okay. Thank you, Leah. And thank you, everyone. Okay, are we back online?
Yes, we are.
Okay, thank you, Liam. Okay, I hope we didn't have many losses. Okay, so let's move on to the second session, which, as I said, is going to be about entity mining. Let's start first with a couple of very few slides. So I already mentioned earlier that the main approach in entity mining is through a task that is called entity recognition. And the task in the typical fashion, in the typical NLP literature, is defined as locating and classifying entities mentioned in a structured text into predefined entity categories. So the idea is that we have a set of entity categories or entity types, if you like, and we want to detect all the mentions of these entities within a particular piece of text. So in the example that you see in the slide, we have the term Wall Street that indicates the location of Wall Street. We have IBM, which is an organization. We have a system, Watson, which I would say it's wrongly, has been wrongly classified as an organization because in reality it's a piece of software. We have $15 being an entity of type price, etc., etc. Now, from a knowledge graph mining perspective, the task is a bit different. It's that given a set of entity types, then first get an appropriate text corpus and then find all the distinct entities per type within it. But of course, the second formulation is not much different than the first one in the sense that if we manage to find most of the entities that are mentioned in a piece of text, then we can simply take the distinct set of them and use it to populate our entity type. Now, from the 6 mining approaches that I mentioned earlier, I'm going to show how we can define, how we can do it with hand-built patterns and rules, and how we can do it with supervised machine learning. And we'll do that by using the tool called Spacey. So let me give you a link. I will put a link in the chat on for the Google Colab notebook. It's view only, so please, if you want to follow, just make a copy in your own drive, and if you want to work on it by yourselves. So I hope, Ilya, can you verify that you can see my notebook?
I can verify.
Okay, thank you. Okay, so forgive me for my sloppy Python, by the way. Okay, so Spacey is, as I said, is a industry strength tool, an open source for that supports basic NLP tasks. And one of the tasks that it supports is named entity recognition. It has a set of models per language, pre-trained machine learning models that have been trained in a supervised way for machine learning, for entity recognition tasks. And this pre-trained system supports the following types of entities. It supports persons, which, as you can see here, this comes from the official description of Spacey, includes all mentions of people, including fictional. So it doesn't make a distinction between real people and fictional people. It supports also nationalities or religious or political groups. It supports identifying buildings, airports, highways, bridges, organizations like companies, agencies, institutions, etc. Location, I think geopolitical entities like countries, cities, and states. locations for non-geopolitical locations like mountain ranges, bodies of water, so rivers, mountains, things like that. Products, excluding services, as they say. Events, but events with a name. So, for example, a sports event, a war, a battle, or a named hurricane. Works of art, law, languages, and then dates, times, and percents. So, and also some additional ones. So, the model that we get, so when we just install Spacie, we immediately get the functionality that, in theory at least, allows us to detect this kind of entities in the text. So its usage is quite simple. So all we need to do is import Spacie. Of course, now we're in Collab here, so Spacie is already installed in the environment. So all we need to do is just import it. And then what we need to do is to load the model, right, by giving the name of the model. So I have a link here that you can follow, and I can actually show you, where you can see for Spacie, for every language that it supports, the available models that it has. Each model has different size, so some models are much larger than others, and other features. So for example, this N-Core Web SM is just 13 megabytes. It contains, it's able to do entity recognition, it's able to do part of speech tagging, so it has some very basic functions. But for instance, it doesn't contain word vector, so it doesn't have this advanced functionality. Whereas this model here, the N-Core Web LG, which is, as you can see, it's 740 megabytes, also contains word vectors, and it has been trained in a much bigger data set, right? And you can also see models for other languages like Greek, where there are actually 3 models, Dutch, English, etc. So coming back, we're going, for the purposes of this tutorial, we're just going to load the symbol, the smallest and the very basic model of English. So as soon as we do that, then we can simply create a function that finds entities in the text. So we call it find entities, create this text. The first thing that we do is that we take the model, which we have named NLP here, we apply its text, and we return an object of type doc. This type doc contains all the linguistic information that Spacie, through the model, has managed to infer from the text. It contains the part of speech, tags, the tokens that the text consists of. But for our task here, we care about the entities that it contains. And these entities are accessible through doc.ents, and we can print the text of the entity, where it starts and where it finishes, and of course the category, the label, the entity type. So as an example here, I have put 3 texts inspired by Apple and Jobs and Wozniak. So for instance, we have the text, Steve Jobs was a genius. Without him, Apple would have never built the iPhone. Steve Wozniak was an expert in computer engineering, and Steve Jobs would never drive a Mercedes. Now, based on the entities entity type that we saw here, what we would expect is for the Spacie system would be to find the people, Steve Jobs and Steve Wozniak as persons, to find the company, Apple, and to find iPhone as a product, right? And perhaps also Mercedes as a product, because in the context here, Mercedes is not the company, but is the product. So if we run this, this is what we get. So from the first text, Spacie induced that Steve Jobs is a person, which is correct. Apple is an organization. but also iPhone is an organization, which is obviously wrong. From the second text, it identified Steve Wozniak correctly, and from the third one, it found Steve Jobs as a person and Mercedes as an organization. Right. So this is what we get from just the existing functionality of Spacey. And of course, we can play further if we want. So, like for example, to see if it identifies more things, like for instance, I don't know, let's find another one. If Jobs, I don't know, had a net worth of, I don't know, 50 million. So if we run this, we find that the word 50 is mentioned as a cardinal, but probably we didn't find the money. You see here that when I put this entity here, 50 million, which I'm not sure if it's completely correct, it didn't manage to find. Anyway, so the main take here is that, remember I said earlier that this is one of the most known systems out there in the market, and you see that already the type of entities that it supports is relatively limited, right? Yeah, and also the granularity lacks a bit. So we can find persons, but we cannot really distinguish between roles of persons, right? We can find organizations, but we cannot. We don't have really support for subtypes of organizations, like for example, financial organizations or non-profit organizations or things like that, right? So in practice, something that in a given project where we don't only have in our schema, in our knowledge graph schema, only these types, we have more. The question that arises is how can we enable the detection of additional entities? That's one question. The other question is how can we improve the accuracy of the system so that when it says iPhone, for example, it doesn't interpret it as an organization, but rather as a product, as it should, in this context at least, right? Or when it finds Mercedes, or when it finds Mercedes, again, it should identify it as a product. So Spacey gives at least two additional ways to expand the coverage with respect to entities and to improve the accuracy of the extraction. The first way is by means of extraction rules, of explicit handmade expansion rules. So let's assume that for our purposes, we want to be able to detect, apart from the entities that we have, to be able to detect also skills. Because you can see in the second text, the term computer engineering is quite interesting and actually denotes a skill. It's a discipline, right? Computer engineering. But in this context, it's a skill, right? Because Steve Wozniak was an expert in computer engineering. So if we were building a knowledge graph about Steve Wozniak as an entity, right, we might need to have this relation that Steve Wozniak was an expert in a skill called knowledge engineering. So the way we can do that is by defining, one way to do that is by defining handmade rules. And this is done in Spacey via a pipe, as part of the pipeline, which is called entity ruler. So we can import this entity ruler, and then we can define patterns and extraction rules by means of a dictionary. Now, here, I have defined two rules. The first rule, the first pattern, says that if you find the term iPhone, then its label is product. So then it it always denotes a product. Obviously, this is not fully correct, right? But I have it here for the sake of demonstration that you can always have that rule. That you can have a rule like if you find this term or this combination of terms, then its entity, it will be recognized as this type of entity. The second rule is about introducing a new type of entity, which is called skill. And as you saw up here, it's not supported from the pre-trained model. And it's a very simple rule. It says that if we have a noun or an adjective, so if there is a term whose part of speech is a noun or adjective, and it is followed by the word engineering, then it should be interpreted as a skill. Again, this is a rule whose accuracy needs to be tested, of course, right? Because it may also give false positives. But nonetheless, it's something that allows us quite easily to expand the basic model of spacey to cover some instantiations of an additional skill. And the interesting thing here is that the very practical thing is that these patterns can then be added within an entity ruler object, which then can be added in the pipeline. So it's not, so we're creating this component here, which has only these two rules in this case, and we add it in the pipe. So then, after we do this, we can rerun the find entities with the model that we have, because now it has been added in the model. And now you can see that iPhone has been identified as a product and computer engineering has been identified as a skill. Of course, these are just two examples of the expressivity of patterns and rules that spacey has. There is a very detailed description of all the ways rule-based matching works on spacey. So there is token matcher, phrase matcher. There is also the ability to use regular expressions. For, I don't know how many of you have used before regular expression. It's a bit of a hate and love relationship. And for the more advanced NLP practitioners, we can also use dependency matching. So parsing the dependency graph of a sentence and then define rules based on that. Yeah, that's it for this part. Are there any questions? I will stop sharing for a while.
We have a raised hand from Aftab again. Hello, Aftab.
Mm-hmm.
You can check the question.
I'm checking the questions after my lesson. Okay. The question by Johannes. If spacey supports just basic NLP, what are the libraries to look for when attempting advanced NLP? What is the difference in your opinion? Yeah, maybe the word basic is not so correct. So spacey, first of all, gives you some foundations, which is really important, right? So basic tasks like part of speech tagging or tokenization and this kind of tasks are usually the basis upon which you start building your own custom solutions, right? Even if you don't use spacey's more advanced libraries like the entity recognition, you can still, in many cases, you will need its tokenization or things like that. There are other libraries that have more advanced things, but what you need to see is what is, if you want to apply this tool in a production environment, and it's not just for experimentation, you need to consider also, how robust it is, how fast it is. That's also a factor, especially if you do this kind of processing in real time. right? That's really important. Question by Bharat. I assume we would need to learn how to use your own custom vocabulary with space for more advanced use cases. Yeah, indeed. So, for example, if you have already gazetteer of terms, if you have an existing set of, I don't know, terms and entities that you want to use, Spacey enables you, allows you to use it. As I said, the examples I gave are really basic. After, if we have a large taxonomy of skills and a corpus of CV, would we follow the approach of custom rule? What would be the approach to map skills in CV to the taxonomy? Okay, so that's a great question. You can use, first of all, indeed, we can use extraction rules. And at XCL, we have used in the past extraction rules. So, for instance, some basic patterns that we see in CVs and vacancies are things like, you know, I'm expert in developing algorithms, or I'm expert in Python. Or we've seen patterns like the word skills, colon, and then skills in a comma separated form, right? So, for example, IT skills or programming skills, colon, and then Python, comma, Java, comma, Jira, I don't know, things like that. So there are patterns. And in many cases, they can give you some quite fast results. Another approach would be to take a bunch of, a set of CVs or vacancies, manually tag, annotate the terms that are skills or are other entities, and then train a machine learning based system. Usually, in the past, it used to be a lot about Markov models and hidden Markov models. Nowadays, you can also use neural networks. Generally, any technique that models sequences, and then you can learn your own entity extractor. And there's no a priori answer which is better. It really depends on how noisy are your data and where you get more accuracy or the quality you want. It's also part of strategy. Do you care about finding to be really accurate in the skills you find in the CV? So you may find less skills, but they're really correct, or you go for quantity, that you want as many keywords as possible, let's say, without, even if some of them are not really important or are not skills at all. A question by Carlos. Can tools like GPT-3 could NLP cloud services improve the accuracy of identity detection? I know that there are efforts, there's a lot of, in the research community, there are a lot of efforts with, I don't know about GPT-3, but with language models for, like BERT, there are a lot of efforts. I don't know I'm not aware of the results. And usually, I mean, there are experiments that show large accuracies, but really the devil is in the details in such cases. How flexible is the approach that you showcase, identifying computer engineering as a skill via custom rule, in contrast to extraction rule that you mentioned? Yeah, so it's just an example, right? So of course, if I put a rule for every engineering or science, etc., it's not that flexible, right? It doesn't scale. That's the problem. In the end, you will end up with a lot of rules, but it's an option. See it like that, right? And it really depends on, let's say, how much in a hurry you are, because generally it's faster to develop. Let's say you have 1 week of development or 2 weeks of development, right? And you want a really accurate system. It's faster. Your bet is more like, okay, I can make some rules that I know that they will work and may not have very high recall. as opposed to spending 1 week just to annotate the data to train a supervised machine learning model. So, of course, it can be that the predefined model already does the work for you. Usually we find keywords in CV. Can we just use keyword search? Yes, but it depends on the task that you want. So if you just want to index some keywords for search purposes, so if your goal is to enable search, most likely you don't need fancy NLP, as you say, right? You need just keywords. But remember that here the task that we're discussing is that we want to find skills to put them in a knowledge graph, and these skills as semantic knowledge to be used elsewhere. So it's not about the CV itself. The CV is just the means to get the skills from. This is the mindset that we have here, right? Because if we start discussing about how at runtime our product takes your CV and analyzes it, I can already tell you that it does it using the knowledge graph. So it's a bit of a chicken and egg problem. Okay, great. Okay, good. So let's continue. Now, so let's say that we don't want to, or we don't want, or we cannot really create more entity rules, more extraction rules. Can we do it in a different way? So Spacey also gives you the opportunity to fine-tune the already trained model with additional training examples. So we saw that before in these examples, the identification of product was not so good. Like, so Mercedes was not really identified as a product as it might should. So we may think that, okay, what we could do is add more examples of texts where an entity is a product. The way we do that is to define a simple dictionary where we have tuples, where we have the text, and then we have the entities, where we specify the beginning and the end of the entity and its type. So in this first example, we say, okay, in the sentence, Walmart is a leading e-commerce company. The entity that starts from 0 to 7, Walmart, is an organization. When we have the text that was driving a BMW, then the entity from 16 to 19 is a product. So in that way, we can define as many training examples as we want. And of course, here I just hard-coded them in the notebook, but imagine that one way to generate this is use some annotation tool like Prodigy, for example, and do the annotation on a text in an intuitive way, and get some JSON data, some data, and then just load the data in this form and then feed them to the model. So it doesn't really matter. But what matters here is to understand that this is a way to give additional examples to the system. So by defining the training data, what we can do is retrain the existing model. How we do that? First of all, we get from the NLP pipeline, so the model, the NER pipe. NER stands for Named Entity Recognition. Now, every time we train a model, in theory, all its pipes are updated. But in this case, we want to disable some of the components and keep only some. So in this case, we only keep the NER component plus some transformer components that may be affected. So we define the unaffected pipes, which are those that are not here. And after we do that, we just train the model. This is standard code that you can find, so it's not something very fancy. What happens is that we train the model for 30 iterations. We randomize the data, that's important. Of course, in this case, they're not a lot. And we update the model. So hopefully, when we do this, and run it again, what happens is in the same data, now Mercedes is identified as a product. So while before Mercedes was identified as an organization, now it is identified as a product, which seems to be an improvement. Of course, we really don't know what has happened in the model. It may be that some things are better, some are worse. So it's really important that every time we do a retraining, that we do a proper evaluation of the changes that have happened. Let me check for questions. Oh, sorry, I think I forgot to share my screen before, right? Yeah, sorry for that. Let me go back. Really sorry. Window, okay. Yeah, so I was saying that, yeah, so these are the trained data. And then what we do is we update the model, and now it is able to identify the Mercedes as a product. So this approach makes sense if mostly if you see that in your own data, the existing model does not work for particular entities as well as you would expect. Also, Spacey gives you the ability, I don't cover it here, but it's easy to find it in its documentation, gives you the ability to build, as it is called a blank model. So a model that has only the algorithm without any pre-trained data, where you can give it your own data. Of course, you would need to give much more data than in this case, and then, but to train your own classifier. Okay, is there? Okay. Now, additionally, if we want to support a new entity that it's not supported, let's say, for instance, food. So let's say that we want to be able, when it says Steve Wozniak enjoyed eating sushi, to be able to identify sushi as food. We can do something similar. We can define additional training data in exactly the same way as before. And the only main difference, so the code remains the same. The main difference is that we need to add this label to the NER pipe so that it knows that, there is this entity type, this new entity type called food. And an additional step that Spacey requires is to create, as it calls here, an optimizer. And that's it. When we do that, this, depending on the size of the data, can take some time. So now you can see that when it says I ate sushi yesterday or Maggi is a common fast food, it's able to find sushi and Maggi as entities of food. Now, something really important. The quality of the machine learning component here is highly dependent on the quality of the input data that we give it, and especially of the annotations. And you will I don't know if any of you has ever run executed an annotation project like this, either themselves or by having to coordinate and guide a number of annotators, or sometimes even worse, through crowdsourcing. But it can be that some entities can be really ambiguous with respect to whether they are indeed, with respect to whether they exist in the data and in the text or not. So, for instance, here in Steve Jobs would never drive a Mercedes. To say that Mercedes is a product, some people may disagree on that, right? Yeah, there are also other types of entities that we may have issues. So it's really critical how we do the annotation. So generally, the quality of the input data. Okay. Any questions? Stop sharing.
We have a raised hand from Mike. Any way to automate the construction of the training data? I think, Mike, that's the question.
Yeah. So self-learning, right? Yeah. So remember in some slides before, I mentioned the tasks of semi-supervised learning and distance supervision, right? So let's take semi-supervised learning. So in semi-supervised learning, what would happen is that instead of, I don't know, annotating 1,000 documents with all the entities that they contain, because usually that's the number that, at least for some types of entities, that you need in order to train a proper model. Instead of doing that, imagine that you annotate just 50 documents, so much less work. The way reinforcement learning, not reinforcement, sorry, semi-supervised learning works is that it takes this seed label data and it runs, it trains a first model, and then it applies it in new data, in unknown data. From the new data that it automatically annotates with entities, it takes only those with the highest confidence. And those, it uses them, it assumes that they are correct or mostly correct, and it uses them as training data for a bigger model. So the idea is that, so it starts with some seed manual data and it continues with in an automatic way. This can go well or can go bad, right? Because usually the problem, and I mentioned that in my book somewhere, is that it can be that if in the beginning there is some error that is not captured, this error may be propagated and may become even bigger and even more systematic. So it might not work. Yeah, exactly what Carlos said. The tiny errors can propagate. So yeah. So I'm not expert in semi-supervision. I know that the algorithms try to mitigate this risk. This is the effort in this kind of research. But again, you will have to see how successful they do that. Joe's question, what would be the top indicator of an entity being too abstract from an R model? I'm not sure I understand the question. Maybe you can rephrase it or elaborate a bit with an example. Yeah, okay. So I think what you're saying is how can we predict, let's say, if an entity is going to be easily or not so easily identified from an error perspective, right? So I think one way to think it from a semantic point of view is the ambiguity of the terms of the entity, of the different entities with respect to the entity types. To give you an example, in TextShare we want to be able to find skills, as I mentioned, right? So one skill is human resources. So imagine that is recruitment. So imagine that you have a job vacancy about a recruiter, and she says, okay, we need someone who has 10 years of experience in recruitment, right? Fair enough. At the same time, many vacancies in the text say that have a note that say, if you have more questions about the position, please contact the recruitment team. So in that case, the term recruitment is not really a skill. The entity type is not skill, it's something else. It's still the same concept. It's about the concept of recruitment, but it doesn't really play the role of a skill, right? So one first indication about this is how many different meanings this entity has with respect to its type, right? So what is the ambiguity with respect to different types? That's one thing. Also, there are, to give you the example in companies can be quite difficult because some companies have very names that are just adjectives, right? So you have a company called Factual, for example, right? When you see that, and of course, companies also many times are written with a capital letter, capitalized. But when that doesn't happen, you have ambiguity, right? So one good indicator before you even try to, so let's say that you have your entities and you want to evaluate how difficult will be to find them in an error scenario, right? You can the easiest way is to run an error for these entities and see how much errors you get. If you get a lot of errors, it means they're quite ambiguous with that respect. By the way, about human names, try, if you have time, play with spacing in these models and try to put in English non-English names and see what happens. Does the training support abbreviations, or do you just have to repeat the sentence with a different start end for the abbreviation? That's a great question, and this actually is more about the relation. It's about the synonym that I mentioned before. So the NER itself, at least the way Spacey does it, doesn't try to detect, doesn't try to put an identity to the entities. So for instance, if it says the United Nations did that, I don't know, and then in the next sentence, the UN did that, did the other, the NER system will not tell you that UN and United Nations are the same entity. So a kind of co-reference resolution, let's say. This is a slightly different task. Carlos, this tool looks interesting for multilingual NLP. Yeah, mm-hmm. Okay, a question by Zan. Is it a good approach to put tags in documents that will be analyzed by NLP? Will it help the NLP processing? For example, to analyze the content of business cases for the creation of information systems. The tags could be business, process, component, service, server, project name. Okay, so tagging, when we have a text, we can tag it in two ways. We can tag it as a whole. So for example, we can have an article and say this article is about, I don't know, politics and religion. So categorization. Or we can go into the text and identify particular spans that denote, that have some categories. Words, compound terms, or sentences. Right. This can be done manually or automatically. In most of the cases, we want to do it automatically. This is why we build classifiers and why we build such systems from an NLP perspective. If we do it manually, it can be used, of course, again, by the end system for whatever purpose, for indexing, for search, etc. And it can be used, perhaps, for training a system to do that automatically later on, right? Independently about knowledge graph. So this is not a question about knowledge graph, right? It's about NLP in general. So it's not about good approach or bad. It's about whether you need those tags and how you're going to put it and what level of error you are good with. Because it can be really cumbersome. And in some cases, you can also get this kind of tags by your end users, right? Some kind of, in a way that this not a robot works or something like that. Okay. Any other question? Actually, I have a question. Is there any entity type that in your scenarios you have difficulty in defining in your knowledge graphs if you use them? And that you would like to automate their population? Software. That's software. It's nice that you say software. Software is one of the big problems that we have at TextChannel, because every day almost we have new libraries and things that programmers put in their CVs that we've never seen them before, and that usually have these funny ambiguous names, right? Because as we probably know, technologies are really creative when they define names for their artifacts. So it is a difficult thing. And also from a semantic perspective, one question is, what kind of granularity do you support? So for example, if you have, I don't know, a Windows operating system, are you trying to find all its possible versions that exist out there? Temporal financial metrics, indeed. Yeah, legislation, legal entity extraction, and there is, by the way, Konstantina, for legislation there are some Greek groups that do a lot of work, especially with Greek legislation. I don't know where you work and where you come from, but I know Alexopoulos from the Athens University of Business and Economics does a lot of work in this kind of entities, and also Manos Koubarakis from the University of Athens. Does space also, after questions, Panos, is there a schema available that explains how Spacey labels different entities? For example, BMW is labeled as a product. Does Spacey also capture documents that is an automobile product? I think it's what I showed earlier. It doesn't have a more elaborate schema. The main entity types that it supports are those that you saw in the table that I have in the notebook. And that's the thing, that, as I said, when it comes to taking more specialized types of entities, there's not, well, you need to build your own, usually, system to do that. It's not, because then it comes down to the distinction between automobile products versus other types of products. Okay, if there is no other question, I think we can go on a break. I mean, I don't know if you're all staying for the next two parts, but if for anyone who's not staying for the next two parts, I hope this was really useful for you, and really thank you for attending.